So I'm finally getting around to making a video introducing and summarizing my progress so far on attempting to hover and land a rocket. I think there are exactly two types of people who do this, either professional engineers with a budget team and good motivation behind doing it, and completely naive amateurs like myself who get into this thinking it'll be a quick weekend project and turns out to be a lot harder than that. Because I didn't realize how long or involved this process was going to be, I haven't done a great job of documenting what I've done so far. So this video is really just a hodgepodge of pictures and schematics I could put together to show where I started thinking how simple this was going to be, and my slow realization of how very wrong I was and what's going to be involved in making this actually work. So hopefully this will be a good primer for anyone thinking about getting into this sort of project. So this is just a quick schematic of my general design for this rocket. For a propellant, I'm going to be using high pressure air stored at 4,500 psi. I like this approach because it gives a very deep and precise throttle ability, and it can also be made using mostly off-the-shelf airsoft parts, which are readily available, light and ruggedized, making them pretty good for this application. The second half is a gimbal bearing of my own design that's going to be driven by linear actuators, which I'm hoping will give the precise mechanical control needed for for stable hover and landing. The design is of course always changing, but right now I've got the final mass at about 2.4 kilograms with all the plumbing and things added in there. And so this tank should be good for about 10 seconds of hover, and that's just assuming basically a constant thrust of what's that, about 25 newtons to keep a hover. It would be capable of a lot more than that, but I definitely want to keep the thrust quite low for these tests. I never really want it to go over about a meter or so. And so, given my goal of just a low and slow hover, the mass is a feature, not a flaw. As long as it can produce enough thrust to get it off the ground, that's really all I need. And basically, the heavier these things are, the easier they are to balance. And so I'm not trying to reduce that weight any. Everything shows so far that I should be able to get enough thrust out of this tank to achieve my goal. Even if it gets a little bit heavier than that. So so far I'm pretty happy with the general design characteristics of it as far as its theoretical ability to do what I want it to do. And just as a safety note, there's going to be some hard stop mechanical limits on the throttle just to make sure it's physically impossible to ever throttle more than about that 25 to 30 Newton range that I'm aiming for. And so I wanted to start by taking a quick look at my propulsion system. This is still pretty much completely conceptual and in no way reflective of what the final components are going to be. I've got a tremendous amount of respect for the energy being contained in here, and my designs so far at best were inefficient and at worst could have killed me. So I am seeking some more qualified help for designing that system when that time comes. But this should still give you an idea of the gist of what I'm doing. The pressure vessel, which is right now designed as an airsoft tank on top, going into a adjustable screw valve that will eventually terminate in a better designed nozzle. With that being controlled by some kind of servo or a stepper motor. With a feedback loop system. I showed here as an IR sensor, but I'll probably be using a 9 degree of freedom IMU in the end rather than just measuring vertical distance. Now the thought here with this design was that I would strap it to a piece of iron pipe and use a closed loop control system to throttle it up and down along that pipe to hold a constant height. And that's still the basic scheme I'm going for with this, but it's become pretty obvious that an iron pipe in PVC with some clamps on there is not going to give the precision and ease of motion I need. So I'll have to redesign this eventually, but that should still give you an idea of the of basically what I'm trying to do with this in the end. So this was the first thing I came up with for a pressure control system. It's massively heavy and clearly not appropriate for flight hardware. But everything was at least appropriately pressure rated, and some of it I had laying around already. So it was a decent place to start to at least just get some idea of how the system was going to work. So despite this hardware all being off the shelf, pressure rated, I'm still, I believe, appropriately paranoid about the energies I'm working with here. I think I had it around a 250,000 joules at full pressure in this tank. So even though I know kids run around with these pressure vessels in the woods all the time, dropping them thinking nothing about it, I'm still quite concerned about that. So I'm taking this pressure system testing very serious. So with that in mind, I did go ahead and build a containment box for pressurizing and testing this with a pretty rudimentary test stand that the pressure vessel attaches to and slides inside with a port, so I can pressurize it from within that shielded box, just in case anything were to go wrong. That's repurposed from another project I was working on before and a bit of a pain in the butt to use, so I would like to redesign that for future tests. So far I've only done a couple of low pressure tests, really just testing out the test stand. The issue here is the mass flow rate through the airsoft regulator, which is going to be fundamentally limiting as it's designed for a different use. And so that's my major issue right now with the pressure system, is coming up with a safe alternative to a airsoft regulator that will give me the flow I need without compromising the safety of a commercial part. But even with that, I was able to get a pretty clean thrust curve from about an 800 psi test. Just showing proof of concept that this design has some teeth to it. Yeah, so my genius solution to this mass flow problem was to bore out the regulator, basically turning into a fitting. I very quickly realized this is a terrible idea. Do not do this. So I'm scrapping this plan until I can find some more qualified help designing this properly. So that's basically where the pressure system sits right now, is just waiting for me to figure out a better solution for adapting the HPA tank to high pressure fittings. It looks like they really don't want you doing that because I've yet to find an appropriate fitting off the shelf for that. So if anyone knows a solution or has an idea for how to properly address this, please feel free to let me know. So even though I don't have the plumbing totally worked out yet, I've done some very conservative estimates on performance from this system, and I'm getting a specific impulse of about 32 seconds, which is, I think, realistically poorer than the commercial performance about 75 seconds, which I believe that's vacuum, and this is obviously working at 1 atmosphere. I'm pretty sure I'll be able to do better than that, but for now, before sinking so much time into this, I wanted to be confident that even worst case scenario, I would be able to achieve what I'm going for here. So with that, I'm pretty confident that the pressure system will come along, but I'm putting that on the back burner for now while I work on the thrust vector control system. For this, I'm going with a gimbal bearing driven by linear actuators. I've seen quite a few onion gimbal designs driven by 9-gram hobby servos, And from working with those myself, I just don't see that being able to give the mechanical stability and performance needed for this application. Um, that is going to come at the expense of a slower response time and frequency of sweep of those from those actuators. But with the very high and fairly large magnitude of center of mass on this design, I don't believe it should need the same frequency provided by a rotational servo, and that these slower linear actuators will be a better choice in the end, just due to their more precise motion and better hold than you can get from those hobby servos. Because I haven't really seen anyone else try this approach on the amateur scale, I'm kind of flying in the dark here on how to build this. So really the only design information I have are from a couple of pictures lifted, one from a NASA publication and one from, I forget what engine this is showing being assembled, but at least giving some kind of idea for the geometry of these linear actuators and how to turn that linear motion into the kind of rotational motion needed for gimbaling. That makes these two pictures really the only design guidance I have, and everything else from there has been first trial and error, and now finally breaking down and turning into math. So I think I'm making some progress on it, but I have a few designs I want to show you just to show where I've been and where it's going. So my goal for this system is really to build it as a balance spot right now, treating it as a 2 degree of freedom inverted pendulum. Which I know is not the best model for the forces of a hovering rocket, but the control loops and mechanical motion are pretty comparable. And actually, this is arguably a harder goal than doing it with a actual thrust vector to provide additional force. And so I figure if I can achieve balance with this system on the ground, or at least close to it, that's sort of my go no-go decision for switching back to working on the pressure system, which is probably going to cost a little bit of money. So I want to be confident that I can control it before I try and build that out. My idea for testing this is really to replace the nozzle, or where the nozzle will be on the rocket, with a half sphere, and then use the actuators to shift the tank that'll be sitting above it, the pressure vessel, to alter the center of mass as the structure leans, and using that as my control system for maintaining vertical stability. Which again, not the perfect model for a rocket in flight, but the best I can do, and in itself a pretty fun project, even if this never translates to a hovering rocket. So this is where I wish I'd done a better job documenting the iterative design of my thrust vector system, because most things with this project, it is turning out to be much harder than I thought, and I'm sure others could learn from my progress on it. But this should still give you a pretty good idea of where I started with this and where it's heading. This is the very first design I came up with. Really did not consider the geometry or motion of it whatsoever, but just looking for something that could get a gimbal rotating, and then shown kind of as a mock-up, just with the tank on top, to see how it's all going to come together. And that tank's a very crucial part of this testing system, because that tank is what provides basically all of the mass that is being used to balance the rocket. I don't really have much to show in the way of testing this one. It basically tore itself apart due to poor programming and poor mechanical design before I was even able to get a video of it. But certainly showed me a few places for improvement for the next iteration. So this is the next major iteration in design. I beefed it up substantially, and at least put some thought into the geometry of it. to try and address some of the problems before, and at least make it impossible for it to tear itself apart if I have a bad software setting. And I knew there were some issues with this one mechanically, but for where I am in my learning right now, I certainly get more out of actually playing with a physical model and seeing and feeling how it works than I can out of a geometric model or even something in FreeCAD. And also really wanted to start playing with the PID loops that will control this and working on getting the IMU integrated into that system and seeing how all that was going to come together. And I did want to make a note about the IMU I'm using. It's a 9 Degree of Freedom from Adafruit. I got off of Amazon for it's about $40. I think the price has dropped now. But what I love about this is it actually calculates absolute orientation itself, which is simply something that's beyond my ability to do right now, and I've got enough things to worry about learning right now without doing that. And it works beautifully with very little intervention on my part. So if you're looking for a easy off-the-shelf way to calculate absolute orientation, I would certainly recommend this unit. Yeah, so despite knowing there are some issues with it, it's still given me a chance to do my first actual PID tuning on the live hardware. I didn't expect this to work, and in fact, I basically can't work without the pressure vessel mounted to the top. But I was actually pretty darn impressed with how close it came on a couple of occasions to maintaining balance, even without having that large mass above it. And so what I really got out of that test was seeing where those issues in the geometry were and what was going to be necessary to fix them. Again, this probably or certainly could have been figured out by looking at it just geometrically or in FreeCAD, but it took a live model for me to see it. So I went back to the drawing board and really put in the effort to actually calculate out how this thing is going to move based on what I need it to do, and came up with what I'm considering, at least if not a optimized, at least a further optimal design that should really improve the performance of it over that previous one. The main thing was figuring out how to get this completely symmetrical in the plus and minus directions of travel, and getting the X and Y axes completely decoupled from each other in their motion. Previously, there's a constraint between them, so as one moved, the other one actually would move with it, which made getting the balance obviously quite tough to do. So this redesign changes all that, and also gives much more speed to it at the sacrifice of a little bit of precision by shortening the moment arms of the actuators as they attach to the gimbal. And so that really brings me to where the project sits right now. I've got some of the new device printed out, and I'm sitting right here by my printer. You may be able to hear it in the background running. But you can see here the new geometry, and I'm thrilled with how it works. It's perfect linear motion for the actuators. It's decoupled, and you'll get a lot more rotation per millimeter of travel from the linear actuation. And so I'm looking forward to getting this up and with the IMU mounted, and seeing how it does compared to the previous. I'm going to try and document these a little bit better now that I'm getting some hardware I'm actually proud to show off. And so hopefully you'll subscribe, and I'll have some decent content coming up over the next few months. Thanks for watching.